Okay, today's topic is passive components, basically film capacitors, and I want to give you a little bit insight and background. So our agenda will be basically a short introduction why I did this presentation and what is the reason and purpose about that. And then the object is a film capacitor, which is a really important role in the moment, especially in the e-mobility world, where we drive with higher power, higher voltages, and lots of currents. And then this is my first test board that I developed by my own. Before that, I always get some from engineering services. But this time I decided to make my own experience. I want to share a little bit the journey of making my own test PCB. And then, of course, we talk about the results, and there's still something left open, so that's the outlook, what I can do in the future, and maybe have more of that. So let's have a short look on the e-mobility, and that's what's going on, and especially about the impact on humans. So imagine for a while everybody has a cell phone, and the broadcast power of the cell phone is about 0.5 watts on a 5G net. So if 87 million inhabitants in Germany theoretically do a cell call at the same time, we end up with 16.4 megawatts. At the same time, we have 60.7 million vehicles. That was in January 2024. And imagine for a second, all of them are BEVs, so somehow driven by electric motors. And there's a rule that's saying probably 10% driving at the same time. Now, instead of having a small battery and accumulator working with 3.3 volt or 3.7 and have a few milliwatts broadcast power, imagine this 10%, the 6 million cars driving with 850 volt and 450 amp peak at frequencies somehow between 5 and 200 kilohertz so far, what I'm seeing in the market. So the message is filtering becomes a very essential topic in the e-mobility industry, especially for the automotive guys, and a lot of such ongoing. And so film capacitors with the filtering property play an important role of that. So what's behind a Tesla? That's my lovely picture. It's a lot of discussion right now about Tesla, but I don't mind so much on the political aspect. So basically, that's a wall box that's behind that. And the wall box, of course, also charges the car with hundreds of volts and tens of amps. And of course, everything is kind of switched mode power supply designs, whatever that is in detail. But basically, it radiates some kind of emission. And so when the automotive industry started 10, 15 years ago, they started to choose safety caps. And what is a safety cap? A safety capacitor, or in German word is Funkinstörer, is a capacitor that's according to standard is called IEC 60384-14. Other known words are Y capacitor, X capacitor, and there are especially X1, Y1, X2, Y2 capacitors. This capacitor originally was developed for grid application. That means it catches up some transients when a flash hits the grid or some big inductive industrial loads get switched on and off. So, and then the transient should be taken off from the device. So, and basically the approach is that it's a single or maybe tens or hundreds of events over lifetime. But it was never really developed to be on a battery electric-driven car with HV plus, HV minus, 800 volt on a DC voltage, basically. And then, of course, they have a constant current that's driving through this X and Y caps. Y caps, I think that's the reason why they choose this. Basically, is a fail-open capacitor. You can imagine if a Y cap goes short, then probably it could hurt or even be a little effect on humans in that case. So there must be a special design that these capacitors don't fail open. And I think we saw that in the presentation in the morning a couple of times, so I will not spend too much time on this. A typical kind of filter, so you have just X capacitor and Y capacitors. Basically, it could be on the battery, from the battery line HV plus, HV minus to the chassis of the car, or to the neutral, or from the face to the protective earth in the grid. So both is possible depending on your OBC application, or is something that drives the inverter system within the car. So there are some standards in place how to define the electrical property. So basically, capacitance is well defined, so 1 kilohertz and 1 volt RMS. There's no DC bias, which caused a lot of discussion with when you start using MLCC's class 2, and I did a presentation for it some years ago. But it's not really a big problem, the no DC bias for film capacitors. Then the dissipation factor, in Europe we say also tangent delta, is defined at 1 kilohertz. ESR is determined at 100 kilohertz, not at 1 kilohertz, because you can calculate from DF and knowing this, the capacitance, of course, also the ESR at 1 kilohertz, but that's a different value. But, and that's the major point, is there's no standard for ESL measurements. And basically, that's because there is some portion in this measurement that's out of our scope. So the definition basically is the area inside the current loop that defines somehow the inductance. But the component is only a part of the whole loop, so we don't have any influence on what you as a customer are doing with those things. And you see here that there could be a tremendous difference depending on the frequency you're looking at. So the same stuff could be at like 6.8 microhenry at 30 kilohertz, and basically going up to 72 picohenry if you go to higher frequencies. That's something that's really confusing at times. So that's the reason why I want to deal a little bit with the ESL and also with ESR, because that has also an impact on this property of the filter at all. So why we were targeting low ESL? As a user capacitor, basically in the DC links, number and X and Y caps, of course, the ESL has an impact on the resonance frequency, and we heard earlier how that is defined. And also, it caused some ringing in the switch application that could be an inverter or a PFC we show earlier this day in some presentation. So how does that look like? That is something we get from the customer. So basically, it's something that's switched, and you see the oscillation that happens because of the inductance inherently in the system. And of course, one part of that is the capacitor with all these properties behind that. And if the problem that we see, or the automotive industry at the moment, is that there are some caps failed in this special position in the circuit, in the Y caps. And that's basically because of they never was designed for this continuous application, or continuous seeing that high currents in this leakage current that coming from the HV plus, HV minus to the chassis ground. So if you do this, or you transform this, the waveform that's recorded by an oscilloscope into an FFT, and then you see something that's a little bit unusual. So you see the basic frequency, and then the higher harmonics that going with the amplitude down, and then you see at a higher frequency, probably something between 1 and 2.5 megahertz, you see a big peak here. That's basically coming from the commutation. So the way how the bridge switches and creates a phase currents for the motor. The important thing is, and what happens in the past is that, of course, the effective, the RMS, the root mean square current, is easily to measure. There are a lot of devices that can do that. But to get the self-heating correct calculated, you need the ESR. And ESR depends on frequency and temperature. And that is where typically somewhere you struggle. And then there's the thermal resistance. The thermal resistance is a pretty stable property, because it's basically somehow to do with the mass and the geometry or the dimensions of the component. But what you can see, I don't know that the relation. So basically, if I take all this higher harmonics, the whole frequency spectrum, I would end up with a total current through the capacitor with 2.622 amps, while if what was typically done in the past only use 7 harmonics, I end up with 335 milliamp, which is a huge difference. And this is one of the reasons why we need to deal and we need to be better in terms of how can we do the simulation and getting ESR correct for different frequencies, in that case for the whole frequency range. So that is the topic. And let's talk a little bit about the film capacitor. So what you see here is so-called a boxed capacitor, the radial one. It has the, it has a winding that's typically in, I don't know, 90% of all cases, that's polypropylene. That get metallized with aluminum for DC or zinc aluminum for AC application. Basically, that's the surface is around something between 20 to 50 nanometer, and the polypropylene film is something in a range of a couple of tens of micrometers, basically. Then, because you need to have a contact here to the windings, so basically there is a metallized layer that will be applied on the left and right side or crown side of the winding, or we call that bobbin. And this is called shoe page layer. So the trick is really to deploy the spread liquid metal on a plastic material that typically melted in the 130, 150 degrees Celsius. So that's not an easy process. It also means you cannot make it unlimited thick, which also limits somehow the contact that you have to apply to get some kind of termination. In this case, it's wire, but there's also some kind of called busbar that happens for the big DC and DC link capacitors. So the wire could not be unlimited big. So that means we have a certain resistance that gives the resistance from the wire into the winding, or we call it bobbin element, basically. And you see here that's a weak point. So the current goes in here. Goes in here and then goes through the capacitor in this area. So when you start this kind of development, what happens? So of course you look in the catalog, and what you get in the catalog, basically you get some kind of ESL and ESR values, but that's a very rough estimation. So you get something that is at 10 kilohertz at 70 degrees C, typically ESR is getting lower with increased temperature, and we get an ESL value. But the question is, what kind of ESL value is that at which frequency? And how does it apply to your application parameters? So you had probably switched at 50 kilohertz or 30 kilohertz, whatever, and your temperature is probably not 70, it's about 80, 85 or 90, so what will be the impact for you? Also, keep an eye on this voltage derating thing. That means we have some room for shifting the rated voltage, or vice versa. You cannot use the component at its rated voltage at higher temperature, so you have to derate. You see here, basically that NDC is defined at 70 degrees, that you have 1100 volts, and when you go at 85, it's only 900 volt, and if you go to 105, which is the maximum temperature, you ended up with 700 volt DC. So something that looks on the first view pretty simple, but it starts out to be pretty time consuming when you want to figure out the right component. The wire plays an important part because everybody heard about or is dealing with this wide band gap semiconductor thing. So that means we increasing the switching frequency, which has a certain impact on the wire. I think everybody's aware about the skin effect, and so basically that reduces the cross section of the wire, and at the same time the impedance goes up, so you have an additional resistance that you have to consider. And this resistance that goes from wire to this shoe page layer could create a kind of hotspot. That's basically also the limitation for the DVDT, which caused, multiply with the capacitance, the peak current. And if the peak current is going too high, then you can have a hotspot or create a hotspot in this area between the wire and this shoe page layer, and that could probably fail your application. So when I was in university, I was skin effect something that happens in the megahertz and gigahertz range. But actually, if I do the math with what I get from my friends in Italy from the plant, it looks a little bit different. Basically, it started at 50 kilohertz. You already lose 15% of your wire. So what I did here is I estimate you use a copper wire, pure copper wire. As soon as you use something with steel copper or copper-cladded core, then you have to consider also the permittivity of the wire, permeability of the wire, not permittivity, the permeability. So you got a μr that's basically to have some impact. But in this table, it's just about a pure copper wire. And then you see at 100 kilohertz, you have already loss of 32%. That means the wire is not, if you use 1.0 millimeter, it's not anymore 1.0 millimeter, it's 0.68 millimeter. And at 100 kilohertz, you nearly lose half of the diameter, which has certain impact. Of course, there's a relation between the length of the wire and the length and the diameter of the wire, which causes a certain impact on ESL. So that means the wire has a significant influence on the performance of the capacitor. And what I did basically is, so I used the raw bobbin without encapsulation, without any kind of box, and then build a lot of samples. So basically, the standard capacitor is on the left side, so that's what you typically get when you buy something. And then we have something that's called low profile. That means we basically flip the bobbin by 90 degrees and then attach the wire in a different direction so that you have a really low height solution on that. And of course, on the left side, it's a little bit tricky to attach more than one wire because the bobbin itself is pretty small. But if you flip it by 90 degrees, then you can have one wire, two wire, or even three wire. And the next thing is that we in Yageo are thinking about press fit contacts, because the soldering is always a topic of discussion with customers. So you have either to use selective soldering, or you have to use very carefully adjust your IR reflow profile. That's not easy. So press fit would probably give you an option to get around all these thermal aspects that happen during manufacturing on your side with the PCB. So in the discussion that I have with the R&D guys in the automotive industry, sometimes I figured out there's a lot of maybe not really basic fundamental things. So people using an LCR meter or using a VNA, but keep in mind, so we don't measure, even it shows and displays the capacitance and the inductance, it's not measuring that. It's basically what the VNA is doing as a Bode 100 is you measure current and voltage and the phase between them. And all the rest is basically mass. So what does it mean is, if you have the imaginary part of the complex impedance, then you have the portion that's defined by the inductance and by the capacitance, but there's only two equations, so you cannot really know which portion is XL and XC. The only thing what you really can see is the phase. So if the phase shifted, then it behaves like an inductor or capacitor, depending if you plus or minus 90 degree or going in this minus or plus area in the phase. So that is something people should have in mind. So does it really matter? So does it make us cause some problem for us? I don't really think about that. So basically, if I take a capacitor with 5 microfarad and 20 nanohenry and all these film capacitors, in a single or double digit ESR milliohm range, if you do the math, and that everybody knows probably, yeah, you end up with, for 1 kilohertz, you ended up with an XC with 31.8 ohm, while the inductive portion is 126 micro ohm. That's basically 5 decades between them. So I would say in practice, it doesn't really matter. So if you go along with the frequency and you increase the frequency, then you see it flips over. So at 10 kilohertz, so you shift it by 1 digit in the certain direction. So for the inductance, then you get a 1.26 milliohm, while your XC decreased from 31.8 to 3.18, and so on and so forth. So there is an area where this basically equal, and then of course you have the self-resonance frequency, and above then the XL portion matters more than the capacitance, and that is also what Arturo showed in the earlier presentation this day. So when we all know, so we have certain capacitance, resistance, inductance, and you want to start to do something with the VNA and try to figure out certain values. So the VNA and the Bode software gives you the ESR, and then you can do the math with the inductance and the capacitance. So ESL basically depends on the length width of the chip. That's basically nothing that changed with the frequency, of course, while the capacitance that based on some kind of physical effects, in the material, you can therefore change at higher frequencies. Because all the stuff that we are using in a capacitor is ferroelectric, is no ferroelectric material, except you use steel-cladded wire, but basically it's not. So the ESL really depends only on the length of on the geometry or dimensions of the chip. And then ESL obviously impacts the self-resonance frequency, and that what we also saw really earlier on that case. So if we want to do a test board like I do and want to define a little bit more better the application-specific values, so how do I start? Basically, Yageo has this simulation tool on the web that is public, and you can access and get it from the website. And so you can see on the x-axis you get a frequency, and then you have the impedance and ESR on the y-axis. So, and you see you can compare different capacitors, you can choose whatever you want, and you can also add bias and temperature. Bias doesn't really matter, you see that. You can give it a try. I'll send you the link and do your own experience with that. But temperature, of course, has a certain impact on that, but it's not that big for polypropylene. It's somehow reasonable. And compared to the impedance, it just changed basically the ESR, but not the overall impedance in the frequency range that's relevant for my application. And I defined that from 1 kilohertz going up to 2 megahertz. That's basically where the power electronic stuff is running. So from here, I got using the Bode software, and I'm not a daily user of this VNA thing, but I think it's very convenient to switch this measurement method by going through all these options. And then, of course, so my impedance is somewhere in a range between 15 and 300 milliohm, and the ESR between 6 and 100 milliohm. So basically for me, the shunt through portion or the test board would be the best fit when I want to get this, a test done and using the VNA and measuring the components. So I was here in Klaus in January and met Florian. And I came up with the first idea, the first board. And so what's really interesting is, so that basically was, the very rough prototype, the first shot that I did. And of course, what I made is I split it in the middle. So the capacitor is basically between the lower and the upper side. And then in the middle, you see the trench that basically disconnects the two sides of the capacitor, and then see a longer one in the middle here, and that's coming basically from Florian. And I was in the beginning, I was not really, I was a little bit confused. So why we need to do that? Because basically I thought the measurement is done well with the original design. But of course he has much more experience than I have, and then we really figured out that it make a difference, when you build this kind of test board, that you have this kind of trench that forces the current somehow through the capacitor and not going from left to right. So that was my first test board that I designed. That's basically for shunt through. It's an open short load calibration. Then what I did with the load is I used 2 times 100 ohm in parallel to get my 50, because basically it's about the symmetry of the board I would keep. I added an SMA connector, and this layout is symmetric, so that's even the connectors look a little bit strange, but basically it's perfectly symmetric layout. And so when Florian told me about this, the longer one here, so this, about this, decoupled without any coupler in between, I was interested and start discussing with friends and also looked a little bit in the internet, and then I found, okay, so that is basically something that comes from a company that making simulation software, and they had something similar, and I was really astonished, though, that it's always started here with 1 kilohertz, 5 kilohertz. You see a certain impact how current runs through the copper trace, and then the middle is a conductor. So, and the discussion with Florian, so we said, okay, so probably we think about 2 versions, so a narrow slot and a wide slot, and what would be the impact on the measurement at all. So basically, you have the capacitor from left to right, and then the signal is coming from the bottom, and then it goes through the capacitor. Basically, the idea is here's the signal, it's coming here, running through the capacitor, going this way, and then going to the ground. Basically, that was the idea. And I was not really sure about the impact. So, what does it make the difference, or how does it make a difference? So basically, this is the values, and I showed the values to a friend of mine, to Melanie Klenner from KK Prime, and she had a very nice idea to do a simulation what happens with the different versions that I have created here. So what you see, if you have no gap in that, no slot between these 2 capacitors, so the current is basically running through both from one side to the other side. So that's a low impedance path, basically. If you would attach the capacitor, so probably most of the signal was going from top to bottom, or bottom to top, depending on how you connect it. But basically, it's not going through the higher impedance of the capacitor. And what we also find out, in contrast to what I found in the internet earlier, is that the frequency that I'm interested in doesn't really matter. You see it looks pretty similar, so it doesn't really make a big difference. If you use a 10 kilohertz, 100 kilohertz, or even 200 kilohertz, or whatever. So that's something, the outcome of that. So, but this is without any kind of trench. So what happens if we add the trench? So, and then you see there is a difference, and you see how the current, the signal is going through the PCB when you add the slot, and also if you have this small and the narrow and the wideband gap. So basically, the idea that Florian had in the beginning was totally correct. So this slots force more or less the signal going through the capacitor. And also, what we found out that the frequency is an important criteria. So basically, it doesn't matter if you use 10 kilohertz, 100 kilohertz, so the current distribution is not really significant different at these frequencies. And what you also see, I have 3 holes there because I had this 1, 2, and 3 wire that I would like to test. And basically, it really makes sense to use the wider gap for the 2-pin or 3-pin versions, and for the 1-pin each side version, you go with the left version. But what I found out when I did all these measurements, so the error is not really big, or the values doesn't really differentiate more than 10%. So that's the outcome for me, depending on how precise or what accuracy you expect from this kind of development or measurement things. Of course, I think everybody knows this pretty Bode 100 software. I really like that. Also have all these opportunities to put the stuff into the memory and put them in an Excel sheet and do some other math calculation around that. So I run through all this different combination. And what I really like, and one of the ideas was, together with my friends in Italy, basically using the circuit fit to feed our online tool that I showed you earlier, and basically an easier way or more accuracy way to build our capacitors into this online simulation tool. So that was the basically idea, and I really like that. So what I definitely need, I need to dig a little bit more into this equivalent circuit modeling. I use the automatic system, and I had a talk earlier this day with Tobias. So yeah, I think we should come up with some more background, and I'm just give it a try, and I really like it. And I see the error is up to nearly 1 megahertz. It's somehow in a 10% range, which in power electronic is totally acceptable. So we don't need this 0.0 something. Because there are so many things that also play a role on this. I have no idea how that really works, but I think there will be coming some material out in the future, and we're really eager to give it a try and dig a little bit more deeper into this modeling. So, and this modeling thing, it's a pretty cool thing because you also can export that and use it in the SPICE netlist, and I was also interested, so I can use this, our really measured model, and that's what you can also do, and take this data and put it into the next level, and that's basically LT SPICE. It took me a while, a little bit. I was not so familiar with LT SPICE, but basically you can use it one-to-one, this sub-circuit. You have to use, that basically is the text file you get out of the Bode 100 software. Oops, here. And then you have to use the name into the component. Here into the component to make sure that LT SPICE recognizes it. You also have to build your own symbol. So I use a capacitor here and just add Yageo on this. And then you can simply do the simulation here. In that case, I just use 1 volt. And then did an FFT scan out of that. Really exciting. It really flawlessly works perfect once you did it. Once you understand the process, and I think it's really absolutely nice. So now, what are the results? Basically, it's really incredible. So if you flip the component by 90 degrees, you can basically get your ESL down by 56%. It's physically the same product. Basically, it's just the orientation change, and in a dramatic way how you see the property could be impacted just by that. And I'm definitely sure that we in Yageo, we will promote it more, make it more public using the low profile solutions. Also, when you go with the different versions, so the 1-wire standard profile and then 1-wire LP, so that means low profile 2-wire. There is certain impact. Of course, ESR goes down simply because they add more resistance in parallel, so the overall resistance drops. But of course, the portion of the windings, the bobbin element itself, does not change. But of course, the impact of the wire you can see clearly. Also, ESL changes. So if you add more wires, not dramatically, but it's the same principle. So if you add more inductors in parallel, the overall inductance drops. And last but not least, you see that on the switching frequency that also changed depending on the ESL. Except one thing here I figured out, the capacitance was a different value, so it looks not really logic, but basically this is based on the different capacitance value of this specific sample that I had. So what happens was press fit, PF stands for press fit low profile. Yeah, that's basically the experience that I made. So when I did this PCB, I said it's not so complicated. You know, one component SMA connector to resistor. I can do it by my own. What I completely, totally forgot is there's a kind of rest ring. So this doesn't really have an impact when you do a wired, because you add a lot of solder and then you get the connection to the rest of the big copper mass. But if we want to figure out the resistance that's caused by the press fit contact, of course we cannot use it, because basically the contact is only the area where you have this kind of burr that you created when you do this gas-tight connection into the whole of the PCB. So if we would add tin on that or solder on that, it's not working, and I was not able to manage the solder. That just you get this small 0.2 millimeter copperless area overbridged. That was simply not possible for me. So what we definitely do is we will promote, and you see here that if you're looking for something that is going on a lower ESL value, just look for low profile. That means the component at the end of the day has less height than width. That's an easy go, and we also had that in the catalog, but it's hardly visible. But if you look for it, basically it's not a big thing. So wrap up. Basically, it was fun to work on my own test board. Even I use this one I got from the engineering services that we used in the past. But I also understand that's a lot more work than I thought in the beginning, even with just a simple component. It was very helpful to have a community and contact to talk with, so like Florian, like Melanie from Prime, and also my colleagues in Italy. Pressbit will be investigated when I have a new board that unfortunately didn't arrive before the presentation today. And yeah, I think there's a lot more to do on the characterization of components, because Yageo is turning into a kind of second Vishay. So we get capacitor resistors, inductors, EMC transformers. So I think until I get retired, there's a lot of things to do using the VNA. Last but not least, I want to say thank you to Melanie for this excellent simulation of the PCB that gives me the insight. Also Florian for the hints and the support, doing all the things. And my colleagues in Italy, Federico Fantini, Roberto Airi, for the insight, the measurement, and also spent all the time in Italy with me figuring out the special needs here. And with that, thank you very much. And I did it really on time.
Yes, perfect.
I'm getting better and better.
That
Okay.
comes with experience, Axel. And before you retire, you will do it to milliseconds. So thanks a lot for the presentation, Axel. It was very interesting to see what you can think of when measuring a film capacitor.
Yep.
And what the different profile versions do. And yeah, thanks for coming.